Hello, this is the second installment in the series of magnetism and matter. As we had already discussed about the Coulomb's law in magnetostatics, we may well move over to the magnetic field intensity, or even that is known as magnetic flux density, or even magnetic induction vector. So many names. uh, but they mean the same, that is the magnetic field B. Now the magnetic field obviously is the one that is responsible uh, for the for the although the magnetic lines of force are responsible for the magnetic forces to act along, and the field intensity just gives us the impact of a given magnet or a given magnetic pole at a particular distance, just like analogous to the electric field intensity, where we had a charge, and for that charge we were obtaining the field intensity at a point. So in this case, what we have over here is that we have a pole which has this is probably a pole which has a pole strength of qm, and we consider a point P over here from at a distance supposedly r from the given magnetic pole, and we want to find out the magnetic field intensity over there. So what we do is we just take the same method of determining the magnetic field. What we do is we just place a test magnetic charge. This is a test magnetic north pole. Remember, the north pole was analogous to the positive charge in case of electrostatics. Here we have the north pole, and the south pole is analogous to the negative charge. So here we have two pole strength. Now this is the pole that is considered from which the point has been taken where we want to determine the field. But before determining the field, we would like to obtain the force that it will apply on a unit magnetic north pole placed at that point. Now that unit magnetic north pole, if placed at that point, then it would experience a certain force that is equal to mu naught divided by 4 pi times of the qm, that is the pole strength, or the magnetic charge over there, multiplied to the magnetic north pole test north pole, and divided by square of the distance. This is the force that was obtained from the Coulomb's law in magnetostatics, expression of force, and we just take the limits. Now obviously this is directed along the direction of r. The magnetic field intensity at that point can be defined as limiting the north pole to 0, that is the magnetic north pole to 0, and force divided by qmn. This is how we define it, just like the case of electric field. So we take the limits over there, qmn tending to 0, and here we have, instead of we can write the entire expression and put the qmn in the denominator. We have mu naught divided by 4 pi qm qmn for the north pole divided by r squared r cap. So qmn can get cancelled out. Now we set the limit, but there is no qmn over there, so no zeros involved. After using the limit, we can get rid of it. So mu naught divided by 4 pi qm divided by r squared r cap is the magnetic field intensity of the charge of the magnetic charge qm, or the magnetic pole strength of magnitude qm, at a distance r from it, and obviously it is directed along the direction of r. Now, why do we use the term magnetic flux density? Now, remember, in case of magnetic flux, just like the case of electric flux, what we have is the magnetic flux simply can be denoted by phi. B is simply equal to the number of magnetic lines of force linked with a given surface area. So the magnetic flux over here is B dot A, the dot product of B and A. So this is simply equal to BA cos theta. BA cos theta is the magnetic flux, and why then we have the value as magnetic flux density. So B here can be said to be equal to the flux per unit area, obviously cosine of that, because the angle is important in that case, on which along which the lines of force act on a given surface. So the magnetic flux density, which is obviously the magnetic field, is equal to the flux per unit area. Per unit area means we are considering the density, areal density. So that is why we have the magnetic flux density, which is obviously equivalent to the magnetic field intensity that we discussed above. Magnetic induction vector, we will know shortly why it is named so. Now, in case of an external field which is being applied, the external magnetic field, that magnetic field may act on a magnetic material, just like we had discussed previously about the uh, materials inside the earth acquiring the property of magnetism. So as they are exposed to the earth's magnetic field over a huge amount of time, they acquire a permanent magnetic field of their own. They turn to permanent magnets, naturally occurring permanent magnets. So is the case with artificial magnets, which when exposed to an external field which magnetizes it, and thus it acquires the magnetic property. So that means here the magnetic property has been induced into a given magnetic material. So that is why the induction process causes it to have a certain magnetic field of its own, and as a result of that we have the magnetic induction vector B vector. Now, the parameter, there are some other terms that we may discuss right away. That is the magnetizing force, or simply magnetic intensity. Now, the magnetizing force or the magnetic intensity, usually denoted by H vector, it's related to the magnetic induction vector in this way. And why so? Because this is providing the magnetic field or the external magnetic field to any given material which is developing a magnetic intensity of its own. And in case of air or vacuum, we have the permeability to be mu naught tick, for the example in case of a solenoid. So this is probably a solenoid, and it is carrying some current. Then it behaves as a dipole, magnetic dipole, or a bar magnet, and it has a magnetic field intensity. Now, the magnetic field obviously acts within this, taking the consideration of the current that is flowing. We can say that the magnetic field will be developed along this direction, along this line, and then, like just like the case of bar magnets, they will be in loops. This is one of the properties which differs in case of magnetic lines of force when compared to that of the electric lines of force, because these magnetic lines of force are in complete loops, whereas the magnetic electric lines of force are not in complete loops. They are continuous though, but they are never in complete loops. Right. So in this case, with the solenoid acting as a bar magnet, solenoid carrying current, so what we have is that it is air cooled, and it is had there been no current and we would have subjected it to an external field, it would have developed or induced current into it. And as a result of that, it would have induced the magnetic field inside it, and that's why we have the field also to be called as the magnetic induction vector, because that is being induced in the presence of an external field. What I'm saying is that if there is an external field, and probably if it is varying, you'll know why in the next chapter, that is electromagnetic induction. So in this case, when we are considering a solenoid subjected to a varying magnetic field external, this is the magnetizing field which is varying. As a result of that, what happens is that it develops a magnetic dipole moment or magnetic field within it. As a result of that, you have its own field to be acting, and that is B vector, and that has been induced. So that is why we have this to be the magnetic induction vector, which is obviously due to this magnetizing force that is provided, or the magnetic intensity. So we define the magnetic intensity or the magnetizing force simply as the magnetic induction that occurs per unit permeability. Now, this was in case of an air-cooled solenoid, or in case of air or vacuum medium. In case of any other medium, we have the value to be, we have the relation simply to be equal to mu r times of H. Sorry, not mu r, mu. Mu r is the relative permeability. Mu is simply the, let me write that again because it seems like mu naught. It is simply mu for any other medium that is being considered. Now these are some of the relations that we get uh, in this part of the discussion. Further, we have the magnetic or the magnetic dipole when subjected to an external uniform field. Just like the electric dipole, it can experience a certain amount of torque in it. But before that, let us consider, or let us study about the electric dipole moment. So, not the electric but the magnetic dipole moment. Now the magnetic dipole moment is simply denoted by m, and it's a vector quantity. And this magnetic dipole moment, just like the electric dipole moment, is due to the pole strengths that are present over there, qm, qm, which is the same, but obviously the nature is different. This is the north pole and this is the south pole. The polarity in this case is different. The nature was positive or negative in case of the electric charges. Now the magnetic charges, or the magnetic pole strength, for the north pole and the south pole have the same magnitude, and they are supposedly separated by a distance, say 2L. So we define the magnetic dipole moment to be equal to the product of one of the pole strengths or one of the magnetic charges multiplied with the distance that is separating them, which is directed, in this case directed from south to north of the pole. Remember, in case of electric dipoles, we had the lines of force or the dipole moment to be directed from the negative charge to the positive charge, and as I said, the south pole here is analogous to the negative charge and the north pole is analogous to the positive charge. So you have the dipole moment to be acting in the opposite direction. That is, in the opposite means from the south towards the north, within the magnet, of course. This is the case within the magnet. Now outside the magnet, because these magnetic lines of force are a continuous loop, so outside the magnet what you have is they go round and they complete this loop and they re-enter back from the south towards the north, and same is the case along this direction as well. Outside they travel from the north towards the south pole, completing the loop inside from the south towards the north. So this is how the lines of force, the magnetic lines of force, act in a given magnet. Now, with this information available to us, what we can say is we can study the behavior of a magnetic dipole in the presence of a uniform external magnetic field. So magnetic dipole placed in a uniform external magnetic field. Now in this case, when the magnetic dipole is placed in a uniform magnetic field, we have already discussed a similar case in the electrostatic part. So this probably the north pole and this is the south pole, and the north pole obviously experiences a force along that direction, a repulsive one, and the south pole experiences an attractive force. But however, the distance here supposedly is 2L, and the magnetic field that is applied has a magnetic induction B vector acting along that side. Qm is the pole strength, so Qm times of B is the force that is acting along that direction, and Qm times of B is acting along this direction. We can however take the force here to be F dash and here as F, although they are same in magnitude, but obviously they are oppositely directed, so I have denoted them with different notations. That is, the magnitude of F dash and F is obviously the same. Now the angle between this, now the dipole moment, as we discussed just now, is from the south towards the north, and the B vector acts along this direction, that is the external field. So the angle between the dipole moment and the B vector here is theta. So if I drop a perpendicular over here, this gives me the perpendicular distance between these two forces, these two coupling forces. They constitute coupling forces. These two, using another ink, these two constitute the coupling forces. I'm redrawing that. This is the force over here, this is the force over here, and this is the angle theta. So dropping a perpendicular from the top, we have this to be the perpendicular distance between the two forces. Now the perpendicular distance in this case, if the length is simply 2L, this distance will be 2L sine theta. Why do we need that perpendicular distance over here? That's because of the definition of torque. Now the torque acting is equal to the product of either force, because these are the coupling forces F and F dash, product of either force and the perpendicular distance separating the forces. With that done and dusted, what we have is that torque tau is equal to, we'll be considering the magnitude at first, is equal to QMB, that is the force acting, multiplied with the distance between them, that is 2L sine theta. Now remember, QM times of 2L, what we just considered over here, studied over here, is the dipole moment multiplied with B times of sine theta. So we have mb sine theta. With mb sine theta and the torque being a vector quantity, we have the m as a vector quantity, we have a b as a vector quantity, and the result over here, that is the torque acting, that too is a vector quantity. Then with products giving a vector quantity, the products must be cross product. So tau simply is equal to m crossed with b. This is the expression for torque acting on a magnetic dipole placed in a uniform magnetic field. And then we have the expression for the potential energy that is stored within that dipole, if at all it is subjected to some external work that is done on it. Now remember, when we do work on a system, it gets stored into the system in the form of potential energy. So that is what we will be doing. So when twisted by an external agent from an angle theta 1 to theta 2 in the presence of the field, the work done will be how much? Now for a twist through an angle d theta, we have the small amount of work dw, it's a scalar quantity. Tau times of d theta is simply mb sine theta d theta. But when integrated from a certain range of angle, we have the total work done to be the integration of the total work, that is from 0 to w, and that is integrated. M and b can be kept aside because they are constants. Sine theta d theta taken from theta 1 to theta 2, so we have cosine theta but in negative, so minus mb cos theta, that is from theta 1 to theta 2, so minus mb cos theta 2, the upper limit, minus cos theta 1. Now if the first angle is 90 degrees and the second angle to which we are rotating it is 0 degrees, that means we are rotating a dipole from the angle 90 degrees between the external field and the dipole to a certain angle theta, then not 0 theta, to a certain angle theta, then this above expression over here simply changes to minus mb cos theta, and the other cos theta 1 is cos 90, so that can go to 0. So what we have over here is simply m dot b, the dot product of the dipole, magnetic dipole moment, with the magnetic field intensity or the magnetic induction vector. So that's the expression for the work done when an external agent does some work in twisting the magnet through an angle theta from the 90-degree position, which is obviously the zero energy position, because there is no, the value is 0 over there, so we can treat it as a zero energy position, mostly called like that in most of the texts that you would find. Now consider the case of the torque being applied with the value of the torque tau to be equal to mb sine theta. In case of the angle being really small, for theta tending to 0 degrees, we have sine theta to be tending to theta. So what we have is that tau is equal to simply mb theta. Now this torque that we have over here, in case of systems or magnetic needles, this torque is restored back due to the restoring mechanism that is provided to the magnetic needle. and as a result of that we have a restoring torque to be acting. The restoring torque for, say, a magnetic needle. We have many such devices which are influenced by the magnetic field, and they are subjected to a certain torque, but then they restore back to the original line. So this is the restoring torque for supposedly a magnetic needle. Then in that case the needle, the torque, restoring torque in that case is tau r, which is equal to tau, and but the expression for tau r is simply I times of alpha, which is the expression for torque. What is I and alpha? I, this is not the current, but let me write the I as something different. Let me write it like this. This is I, and this is obviously the moment of inertia times the angular acceleration. So the restoring torque in this case, now the angular acceleration can also be expressed as the uh, double derivative of the angle theta with respect to time. That is the angular displacement, the writing it over here, d square theta divided by dt square, that is the double rate of change of the angular displacement theta with respect to time. So this is the expression for restoring torque, and so what we have in this case is I d square theta divided by dt squared is equal to is equal to minus mb theta, because the restoring torque takes it in the opposite sense. So that is why we can include the negative sign, because torque, remember, is a vector quantity. The restoring torque takes it in the opposite direction. Now with this value available to us, the acceleration therefore is equal to the negative of mb divided by the moment of inertia times of theta. Now this expression seems familiar. What this expression says is that the acceleration over here is the negative of the displacement. The angular acceleration is the negative of the angular displacement, which is the case of an SHM system under simple harmonic motion. And what we have in case of simple harmonic motion is that you have a displacement which is equal to the negative of omega square times of the amplitude, or the sorry, not the displacement, the acceleration. The acceleration is simply negative uh, omega squared with r, and omega square from that omega square is simply 2 is the angular frequency. And what we have from the angular frequency is that the angular frequency is equal to 2 pi divided by the time period, right? So again, in this expression we have the angular frequency omega squared, drawing an analogy to what we studied or what we discussed over here. Omega squared is simply mb divided by I. That means 2 pi by t whole squared is equal to mb divided by I, or we get the t can get cross multiplied over there, so we have t square to be equal to 2 pi squared I divided by mb taken to the other side, So finally, we have the expression for a time period of oscillation in that case, and that is simply equal to the root over taken to the other side is 2 pi squared, root over is 2 pi, and that root over of I divided by mb. I, remember, is the moment of inertia of the given device, which is subjected to a torque and then later restored by the restoring torque. So this is the expression for the time period of oscillation that occurs momentarily. This is obviously an ideal oscillation, not an undamped case, but as we know in practical cases, in general cases that we study or we observe, the oscillations are damped ones. But this is just for a smaller angle we take for a smaller interval of time, and thus we have a certain time period for that oscillation as well. Now let me just brief you with something else, that in the space that is available for us at the top and at the bottom over there, we'll be discussing two expressions which we have already discussed in electrostatics, and you can draw the comparison and obtain those formulas all by yourself. Really easy stuff. What we can determine is that the magnetic field intensity in case of a magnetic dipole along the axial line at a distance, which is at a distance, suppose x, from the center of the magnetic dipole. So this magnetic dipole has a length of 2L. So from the center we consider a distance x where we want to obtain the magnetic dipole moment, or sorry, the magnetic field intensity. And just like the electric field intensity, what I'm going to do is I'm going to write the expression straight away and ask you to try it for yourself. You can obviously use the help of the derivation that we have done in the electrostatics video for the field intensity, electric field intensity in case of the axial, along the axial line of a electric dipole, is exactly the same expression, but obviously the parameters are different when considered in case of the magnetic field. So this is mu naught by 4 pi, which is the constant K, which is also the case in electrostatics, and instead it has the epsilon naught to be written in the denominator. So mu 0 divided by 4 pi, and Qm is the magnetic pole strength, and the magnetic dipole moment, as we discussed in this video, is m vector divided by the cube of the distance, that is x cube. This is the expression, and the magnetic induction vector obviously lies along the direction of the magnetic dipole moment in the along the axial line. But in case of the equatorial line, that is along the perpendicular bisector of the dipole, I'm drawing it in the space given in the space available below. So again we take a distance x from the center of a dipole which has the length of 2L, so L and L on either side from the center, and you have, what we need to determine is the magnetic field intensity over here at a distance x from the center. The distance over here is 2L, that of the dipole. So here the magnetic field intensity is simply equal to the negative, and this is 2 factor 2 over there at the top, 2m divided by x cube, and here we have simply mu naught by 4 pi, that is k m divided by x cube. There's no factor 2 over there, and what's new is that it has a negative sign to it. That means if the dipole moment acts from the south towards the north, the field intensity acts along this direction, the net field intensity due to that. So the net field intensity, expressions for the net field intensity in case of the magnetic dipole along the axial and the equatorial line. This is the expression for axial line, and this is the expression for the equatorial line. You can check for yourself with these values. The derivation part is almost, if not completely, equal to or similar to that in case of the electric dipole. So that's it for this video on magnetism and matter, the second installment, and we probably would try and complete most of the portions uh, at this level in the next video. Till then, thank you for watching.